Hello everyone, today we're going to talk about minor and major losses in internal flow. So before we start talking about minor losses, first let's see what we learned so far. First we learn about friction factor. So friction factor that we could use either Halland equation or Moody's diagram. So this is something we learned just in the last lecture. And then we learn, okay, whenever we know friction factor, we can use major loss, right? Major losses. So we always have some energy loss in the system. Some of them called major losses that can be find it from Darcy equation. So it's friction factor, F is friction factor, L is length, V is velocity, D is diameter, and G is gravity. So if we have everything, we can find the amount of head loss we have in the system from point 1 to point 2. To find friction factor, usually we use Halland equation or Moody's diagram. Both of them give you almost the same answer, maybe within 2% different, but it's almost the same answer. First of all, we need to find Reynolds number. Why we need Reynolds number? Because based on Reynolds number range, we can say either it's laminar flow, transitional, or turbulent flow. Most of engineering application is turbulent flow. So this is the Halland equation. So it's F is friction factor. Epsilon is, do you remember what was epsilon or E? It's absolute roughness. And epsilon over D in Moody's diagram was relative roughness. So be careful about terminology. One of them is absolute roughness, the other one is relative roughness. So usually it depends, this is all the equation we use to do all the calculation in piping system. It depends on what is unknown. We can figure out how to use these problems. So usually we have more than one unknown. We don't know the friction factor because we're just about to design the pipe. We don't know the diameter. We don't know the Reynolds number, and that's why, and sometimes we don't know even the flow rate. So based on that, we have more equation, more unknown that we need to employ different way to use this equation and solve the problem. All right. Let's see what is the objective of today's lecture about minor losses. First, we understand the impact of minor losses on distribution system. Maybe when we talk about minor losses, you think minor losses is so small and they are negligible. But the truth is, if you add all these minor losses here and there, sometimes it's even greater than major losses. The second things we learn is develop a method for selecting appropriate minor losses and apply them to the engineering problem. How we can find minor losses. And the third objective is to learn about Hazen and Manning equation. This is very important and it's very applicable, especially in FE exam. All right, let's see what's outlined for today's lecture. First, we discuss pressure zone and PRV and their use in water distribution system. Second things, we are going to classify minor losses and apply them to the example problem. And at the end, we just discuss Hazen and Manning equation and their use in engineering. So we learn about all these pressure zone, minor losses, and Hazen and Manning equation to be able to design a piping system or find a pressure drop or design a pump, or depends on whatever the problem ask us, or in the engineering career we need to find. All right, so let's see what is the pressure zone. Maybe in the water distribution map, you see different color. What does it mean, this color here and there, or just sometimes see uh, zone 1, zone 2, zone 3, zone 4. This is the pressure zone. It means the pressure in each area based on the elevation is different. But we want to experience the same pressure in every single house. We don't want to take a shower somewhere that, you know, the pressure is not good enough. That's why, as an engineer, we are going to design a piping system based on the pressure zones we have. Let's see the reason that minor losses happen. So if you have a valve here, you create a turbulent flow. So some energy between point 1 and point 2 will change. Maybe it turns to heat, or anything else. But the truth is, you lose some energy here, right? That's why it causes some minor losses in this valve. Similarly, in this picture, from point 1 and point 2, when you have a bending, you have minor losses. So let's see what is the main reason of minor loss. So anytime we have a piping system, either because of fittings we have, valves we have, bends, elbow, teeth, inlets, exit, enlargement, and contractions, all of them causes some losses that mainly we call minor losses. All right, let's see how to generally find out what is the minor losses. So if you have a picture like this with sharp edge, for sure you have more losses compared to when it's well-rounded inlet, right? Because of this recirculating flow or turbulent flow that happens here and there, right? That's why we have a greater KL value. What is KL value? It's a minor loss coefficient that we're going to talk about it in a minute. So you can see the coefficient of minor losses in the sharp edge is greater than well-rounded inlet. So previously, we learned how to find drop pressure from point 1 to point 2. We can find the head loss from Darcy equation, then find the pressure drop. What happens if in the middle we have a valve? So plus the major loss we have from point 1 to point 2, we're adding some minor losses. All right. Let's see what is the pressure reducing valve, or PRV, that we use to prevent pressure in some point getting too high. So we want to experience the same pressure. So this is one of these PRVs that we designed to have to change the pressure and control the pressure in the piping system. How we can analyze these PRVs? Usually we use CFD analysis to analyze the flow inside the piping if it's getting very complicated. But for now, a lot of things we can do manually and analyze the system without any software. All right, so why does minor losses occur? Usually because creating disturbance inside the piping system and changing in energy. So minor losses is usually expressed based on velocity head. You are familiar with b squared over 2g, and the velocity we use is always average velocity. So minor head loss is coefficient of head loss, minor losses, multiply velocity head. So anytime we want to find head loss, we might have a lot of minor losses, plus head loss due to friction, or we just call it major head loss. So the total head loss is the combination of minor losses plus head loss due to friction, or just major head loss that we can calculate it from Darcy equation. Let's look at some connection in piping system and see what is this KL value. So in the next step, we are going to introduce what is KL value. Is it something we need to calculate? No, KL or loss coefficient is a manufacturer dependent. So the manufacturer give us the KL value. So you can see it's different for pipe inlet here compared to this one, or in different bands or branches, or here you can see different valve. Here you can see different valve. So valve are very important because usually in any system we have a couple of valve, and in valve it depends on how much they are open or how much they're closed. Maybe the KL value is different compared to when it's fully open. So make sure when we have a valve, you choose the correct KL value. Here is some of the KL value that is very common for entrance. If it's sharp, it's 0.5, or if it's fitting, it's between 0.19 to 10, or if it's contraction, it varies. All right, let's see the equation that we need to find all these losses, either it's minor or it's major. So the total head loss in general is the combination of major loss and minor loss. You already know how to find major loss from Darcy equation. So this is something new that you just learned today. It's minor head loss that depends on the coefficient of minor loss that you need to look at the table in the textbook to find KL value. So the total head loss, if the diameter is the same, you can factor velocity head and use this equation. So either this one or this one is both are correct if you want to use, but make sure the diameter doesn't change if you want to use this one. So it doesn't matter how many pipe we have. Maybe we have a couple of major loss, or we have a couple of minor losses in the system. All right, let's look at some more example of KL value. Get familiar with the textbook tables for KL value. So here you can see based on pipe inlet, we have different KL value. Sometimes it depends on, if it's rounded, it depends on radius to the diameter of the pipe, or sometimes it's alpha, KL is alpha, and just it depends on what type of flow we have. For example, if we have the kinetic energy correction factor is alpha 2, or for laminar flow, and sometimes it's alpha equals 1.05 or just 1 for fully developed turbulent flow. So you already seen this alpha in the energy equation as coefficient of velocity head. All right. What else we have? Sometimes KL value is depends on alpha and also the diameter, if it's sudden expansion or contraction, or you can use the graph, you can find KL based on the diameter, or sometimes based on the data in gradual expansion and contraction. So make sure you use the correct KL values. Let's just look at a couple of more. And again, I'm going to emphasize on valves. So it depends on if it's fully open or how much is closed. We might have different KL value. All right, let's introduce two important equations. First, it's Hazen-Williams equation. So if you want to find the velocity in internal flow where we have some minor losses, we can use this Hazen-Williams equation, which is empirical equation that it's not based on theory, it's based on observation, it's completely empirical equation. It's good for flow in the pipe greater than 2 inches or velocity is less than 10 feet per second. And as you can see, it's usually used in water works in industry. So this is the equation that we have similar things for Hazen-Williams equation in different textbook or FE. You can see different version, but all of them are the same. So this one is the equation that we use in this class. So for British system is different than SI system. So let's see what is here. Velocity equals to this coefficient, and then S stands for a slope. What is a slope? Is head loss due to friction to the L. So if you have like energy grade line, you know how to draw energy grade line, and your hydraulic grade line is somewhere here. You have some drop due to head loss, right? So if the length is L, the slope is, this is the slope, and it's head loss over L. CHW, it's a Hazen coefficient that is varies. There is a table that you can find Hazen coefficient, and RH is hydraulic radius. All right, let's introduce the second equation that is widely in industry and also in FE exam. It's Manning equation to find the velocity. You know, anytime you find the velocity, it's easy to find flow. So anytime you need flow, just you need to multiply velocity by area. So sometime in different textbook you can see another equation for flow, but basically both of them are the same thing. So you can see a new things in this equation, which is N. What is N? It's roughness coefficient. N is roughness coefficient. Again, there is a table. You can find roughness coefficient for Manning equation. S is a slope and RH is hydraulic radius. All right, let's summary what we learned today and then solve an example. So we learn about total head loss. It's major loss plus minor loss. How to find major loss? Yes, with Darcy equation. How to find minor loss? First, find coefficient of losses KL from textbook. So this one comes from table in your textbook in chapter 8. And you are familiar with velocity and G. If the diameter is the same for the whole system, we can just factor velocity head and come up with this equation. Let's solve an example and see how we can use all the information we learned today to calculate the head loss. All right. Here is an example for minor and major losses. Usually this topic is so important in fluid mechanics, so make sure you go over textbook and solve sample problem. If you have any question, just ask me during my virtual office hour. So let's see what is given and what we need to find. Water is to be pumped at 3 feet per second, so the velocity is given. This is velocity from a reservoir into a storage tank using a 3-inch diameter. So the diameter is also given. Diameter pipe that is 50 feet long. So the length for the pipe is also given. Determine the power output for the pump. Okay, so we want to find what is the power for pump. W dot in your textbook, or P for pump. If H is 6 feet, so there's two scenarios. Maybe you can solve the problem for when H is 8 feet, but the problem at this part, you just need to find major and minor loss when H is 6 feet. Take the friction factor 0.025 and include minor losses in the piping system. And also KL value is given for elbow and KL value is given for reentrance. Okay, let's see where we have minor losses. First is elbow. Anytime we have elbow, we have some minor losses. 1 elbow, 2 elbow here, and 3 elbow here. So let me use a highlighter, and here is the third elbow, and here is 4 elbow. So I have 4 elbow and 1 reentrant. So here is a reentrant. So this is all the minor losses I have in the system. Also I have, so here is minor losses. And also I have major losses along the pipe. So minor losses plus major loss. Or think about it, stop the video and think about how you can use the equation that is given to you, which is head loss, energy equation, and all the equation you have to solve this problem to find what is the power for pump. All right, let's see how we can solve this problem with the equation that we have. So the first question is how to find head loss. For head loss, we have major head loss and also minor head loss, right? So let's see what we have. We have a velocity, diameter, length, and friction factor and gamma, you know, for British system is 62.4 pound per cubic feet. So what we need to do is writing Bernoulli's equation as usual between 2 points. What is the best point to write Bernoulli's equation? Correct. Between A and C, we can write Bernoulli's equation because they are open to atmosphere and velocity at A is 0. Let's assume the datum is right here. So here is my datum. Okay, so I write Bernoulli's equation between point A and point C. So between point A and point C, writing the Bernoulli's equation. So what is the pressure at A is 0 because it's open to atmosphere. What is the velocity at A? It's 0 because it's a large surface. What is the elevation? Elevation is also 0. How about point 2 or point C? What's the pressure? It's open to atmosphere, it's 0. What is the velocity at point 2? I don't know. And what is the elevation at point 2 is 7 feet. So I have everything I need. So let's see what is 0 and then solve for what we don't have. So this one is 0. Alpha, what is alpha 1 and alpha 2? If it's not given, it means, and usually we have turbulent flow, we can assume alpha 1 and alpha 2 are equals to 1.05 or just simply assume it's 1. So velocity at point 1 is 0, elevation is 0. I don't know the head for pump. I know pressure at point C is 0. I know the velocity after pumps. So this is the velocity after pump. It's 3 feet per second. Elevation, I know it's 7 feet. Now I'm going to find head loss. What is the total head loss? It's combination of minor and major losses. All right, let's put the number and see what we get. Go ahead and calculate everything and find the head for pump from energy equation. All right, let's see what we have. This one is 0, 0, 0 plus head for pump equals 0 plus 3 feet per second squared over 2. Make sure you put the correct G, 32.2 feet per squared second, plus elevation is 7 feet, plus head loss. So what is the major head loss? Major head loss is this one. So first friction factor, what is friction factor, is 0.025 and it's unitless. What is the length of the pipe is 50 feet. What is the diameter is 3 inch. Make sure you convert it to feet. Multiply velocity, which is 3 feet per second squared over 2 multiply G, which is 32.2. So this is all major loss, okay? So this is all major loss. I still need to add minor losses, right? So I have one reentrance, so it's, let's change this one, it's plus one reentrance. What is the KL value for reentrance is 0.1, 1.0 V squared, so it's 3 feet per second squared over 2G, which is 2 multiplied 32.2. We have 4 elbow, so it's 4. And what is the KL value for elbow? It's 0.9. Let's check if it's 0.9. Yes, it's 0.9. So multiply 3 feet per second squared over 2 multiply G. So what else we have? That's all for minor losses. So this is all minor losses. 1 for reentrance and 4 for elbows. Okay, the only thing that is unknown from here is head for pump. So go ahead and find head for pump. From here, head for pump is 8.481 and the unit for head for pump is feet. So here is head for pump. What the question asked was power for pump. So I'm going to find the power for pump, which is Q gamma head for pump. I know the velocity, but I don't know the flow rate. So anytime I need flow rate, just I need to multiply it by cross-section area. So V is 3 feet per second. Multiply the area is pi radius square. Make sure you convert it to feet. Multiply 62.4 pound feet cubic. Multiply head for pump. So this one is VA, which is Q. All right, so from here, power for pump is 77.94 feet pound per second. If I want to convert this one to horsepower, just I need to divide it by 550, and from here power for pump is 0.142 horsepower. And that's it for today. All right, let's work on some more problem in your homework that is due on Friday. We also have a quiz from minor losses and major loss on Friday. Let's call it a day and have a wonderful rest of the day.